The first wave is the P wave, which represents depolarization and contraction of the atria. The next is the QRS complex, which represents the depolarization and contraction of the ventricles. It is followed by the T wave, representing repolarization of the ventricles. The repolarization of the atria is not recorded on the routine electrocardiograph. Sometimes another small upright wave follows the T wave and is termed as the U wave. Now coming to the QRS complex, the initial downward deflection of the QRS complex is termed as the Q wave. It may or may not be present. The first upward deflection of the QRS complex is termed as the R wave, and the downward deflection following the R wave is termed as the S wave. Sometimes there may be a second upward deflection following an R wave. It is termed as R dash wave. And if a downward deflection occurs after R dash wave, it is termed as S dash wave. Now we shall see a few QRS complexes to understand the terminology better. Here we see a small R wave and a deep S wave, an RS pattern. This is a tall R wave and a deep S wave, another RS pattern. And this is a tall R wave and a small S wave, again an RS pattern. You must have noted by now that prominent waves are written in capital letters and small waves in small letters. This is a R pattern with no Q wave, no S wave. In this complex we see a small Q wave, a tall R wave and a small S wave, a QRS complex. And in this complex there is only a downward deflection, no R wave. We do not know whether it is a Q wave or a S wave, so it is termed as QS complex. This is a RS R dash with a deep S wave. This is a RS R dash with a tall R dash wave. This is a R dash pattern, and this is R dash S dash pattern. Now we shall study the various intervals. The time from the onset of the P wave to the onset of the QRS complex is termed as the PR interval. It represents the conduction time from the atrium to the ventricles, from the onset of P wave to the onset of QRS complex. The time from the beginning of the Q wave to the end of the S wave is called the QRS interval. It indicates the time taken by the impulse to spread through the two ventricles. The time from the beginning of the Q wave to the end of the T wave is called the QT interval. It represents the total electrical activity of the ventricles. The line between the QRS complex and the T wave is termed as the ST segment, and the point of junction between the QRS complex and the ST segment is called the J point. The time interval from the apex of one R wave to the apex of next R wave is termed as the RR interval. RR interval is related to the heart rate or rate of ventricular contractions. The time interval from the beginning of one P wave to the beginning of next P wave is termed as the PP interval. The PP interval indicates the rate of atrial contractions. Under normal circumstances, the RR interval and the PP interval are both equal. In a normal ECG, the PR, ST and TP segments are at the same horizontal level and form the baseline or the isoelectric line. The amplitudes of all the waves are measured from this line. The standard electrocardiograph is a recording made from 12 leads. Each lead records the electrical potential difference between a positive and a negative body surface electrode. And each lead gives us a view of the electrical activity of heart from a different direction. 6 of these leads, that is 1, 2, 3, AVR, AVL and AVF, give different views in the frontal plane, and 6 chest leads V1 to V6 give the views in the horizontal plane. So in effect, we have 3 active electrodes whose combinations will give us 6 leads. 3 bipolar leads, 1, 2 and 3, and 3 unipolar leads, AVR, AVL and AVF. Leads 1, 2 and 3 are bipolar leads and they record the electric potential difference between two extremities at a time. Lead 1, as you can see, records the potential difference between left arm and right arm. Lead 2 records the potential difference between left leg and right arm. And lead 3 records the potential difference between left leg and left arm. Now note the direction of each lead. This is the Einthoven's triangle showing positive terminal of each lead. So lead 1 is directed from the left arm to the right arm. Lead 2 is directed from the left leg to the right arm. And lead 3 is directed from left leg to left arm. Now the directions of each lead are depicted. Red arrow for lead 1, blue arrow for lead 2 and orange for lead 3. Let us now overlap the directions over the heart. And the next diagram will show the leads as to how they look at the heart or the directions from which they look at the heart. Lead 1 from the left side and leads 2 and 3 from the inferior side. All other leads are unipolar leads. The letter V stands for a unipolar lead. So AVR, AVL and AVF are unipolar limb leads, and V1, V2, V3, V4, V5 and V6 are unipolar chest leads. The unipolar limb leads, however, have a very low electric potential, so they are instrumentally augmented by connecting the other two limbs to form the neutral electrode. Hence the letter A is used to designate an augmented lead. Thus AVR means augmented unipolar lead of the right arm. The exploring electrode is on the right arm, while the left arm and leg are connected to the neutral electrode to augment its potential. AVL means augmented unipolar lead of the left arm with exploring electrode on the left arm. And AVF means augmented unipolar lead of the left leg with exploring electrode over the left leg. This diagram now shows how the 6 different limb leads look at the heart from 6 different directions. Leads 1 and AVL from the left side, leads 2, 3 AVF from the inferior side, and lead AVR from the right side. The chest leads are recorded with an exploring electrode placed at various points over the chest, while all the 3 limb electrodes are connected together to form the neutral electrode. The points are marked as follows. Palpate the sternal angle. The space just below the sternal angle is the second intercostal space. Mark the fourth intercostal space at right sternal border as V1. Then mark at the same level, that is in the fourth intercostal space at the left sternal border as V2. Mark V4 in the mid-clavicular line in fifth intercostal space. The point midway between V2 and V4 is V3. Now mark V5 and V6 in the same horizontal level as V4 in the anterior axillary line and mid-axillary line in the 6th and 7th intercostal spaces respectively. Thus we have 6 standard chest leads, and this is a diagrammatic horizontal cross-section of the chest. Observe that the leads V1 and V2 face the right ventricle, V3 faces the interventricular septum, and V4, V5 and V6 face the free wall of the left ventricle. Thus limb leads give different views of the electrical activity of the heart in the frontal plane, and chest leads give different views in horizontal plane. What we must remember always is that lead 1 and AVL are anterior leads directed to the anterior and left wall of the left ventricle, while leads 2, 3 and AVF are inferior wall leads directed to the inferior wall of the left ventricle. Leads 1 and AVL are leads to the anterior wall, and leads 2, 3 AVF are leads to the inferior wall. Now let us overlap the two diagrams, and we find that leads 1, AVL, V5 and V6 are left-sided leads that look at the left side of the heart, while V1 and V2 are right-sided leads that look at the right side of the heart. To revise, leads 1, AVL, V5 and V6 are left-sided leads, and leads V1 and V2 are right-sided leads. Calculation of the heart rate. The heart rate is calculated by measuring the number of small squares between two successive R waves. 1500 divided by this number gives us the heart rate per minute. The standard ECG paper runs at a rate of 25 millimeters per second. So each small square represents 0.04 seconds, and each large square represents 0.2 seconds, and 1500 small squares represent 1 minute. In this ECG, the RR interval measures 10 small squares. So the rate is 1500 divided by 10 equal to 150 per minute. A rate above 100 per minute is termed as tachycardia. In the second ECG, the RR interval is much prolonged. Let us count it, taking help of the large squares in thick lines after every 5 small squares. The RR interval is 28 small squares. So the heart rate is 1500 divided by 28 equal to 54 per minute. A rate below 60 per minute is termed as bradycardia. In this ECG, count the RR interval. It is 18 small squares. So the rate is 84 per minute, that is within normal range. So normally the RR interval should be between 15 to 25 small squares or 60 to 100 per minute. Now in this ECG, the rhythm is irregular. Each RR interval is different. So in this case, count the number of R waves in 15 large squares which represent 3 seconds and multiply the number by 20 to get an approximate heart rate per minute. This tracing shows 5 R waves in 15 large squares. So the rate is about 100 per minute. So before heart rate is calculated, see whether the rhythm is regular. We must also remember that RR interval actually measures the ventricular rate. In total heart block, where P waves do not correspond with the QRS complexes, the atrial rate should be calculated separately by measuring the number of small squares between two P waves and dividing 1500 by this number. In this tracing, the PP interval is 15 small squares and the RR interval is 50 small squares. So the atrial rate is 100 per minute, while ventricular rate is 30 per minute. Clinically, what we count by palpating the pulse is ventricular rate. Atrial rate can be seen only on ECG. Axis deviation. To look for deviation of electrical axis of heart, we must study leads 1 and 3. Normally, QRS complexes are predominantly upwards in both these leads. In left axis deviation, there is a prominent R wave in lead 1 and a prominent negative deflection, either Q or S, in lead 3. In right axis deviation, there is a prominent negative deflection in lead 1 and a prominent R wave in lead 3. To avoid confusion, remember a simple mnemonic: left leaves and right reaches. Imagine lead 1 above and lead 3 below. The QRS complexes seem to leave one another in left axis deviation, that is left leaves, and QRS complexes seem to reach each other in right axis deviation, that is right reaches. This ECG shows left axis deviation. Left axis deviation is seen in left ventricular hypertrophy, left bundle branch block, and inferior wall infarct. This ECG shows right axis deviation. Right axis deviation is seen in right ventricular hypertrophy, right bundle branch block, and anterior wall infarct.